Welcome. This video I'm going to be talking about using Newton's law problems to analyze multiple body problems. So that's multiple body problems are where you maybe put a force on a few objects and they accelerate together, and I want to show you how you can figure out the forces between the objects when that happens. Okay, so to do that I'm going to use Newton's second law and Newton's third law. And so Newton's second law, you may know it as F net equals ma, but and that's what it is. But I would like, for this video, I'd like you to look at it as that the acceleration of a system is equal to the net force on the system divided by the mass of the system. Okay, so we're going to talk about what we mean by a system when we do some of these problems. The other thing is that Newton's third law is, for every force there's an equal and opposite force, or for every action there's a reaction. But I think the most powerful way to know Newton's third law is that if object A pushes or pulls on object B, then object B pushes or pulls on object A with the same force, same size force, but in the exact opposite direction. Okay, so, and for the exact same amount of time. So no object can push on another object more than the other object pushes on the first object. They always are the exact same. Okay. Okay, so with those two things, then let's take a look at a problem. Okay, so we have a problem like this. I'm going to try and make it so that the numbers don't get in our way. So to do that, I've chosen really simple numbers, and we're going to use for g, the acceleration due to gravity, we're going to up it a little bit from 9.8 meters per second squared to 10 meters per second squared, just so that the numbers don't get in our way. AP Physics uses 10 meters per second squared too. So, all right, so what we have is a problem where we're going to put a 12 Newton force on 3 boxes. Now the 3 boxes are sitting on this surface. This table is horizontal and it's frictionless. And there's 2 kilogram, a 3 kilogram, and a 1 kilogram. And the 1 kilogram is held up there by friction. So there is friction between these 2 boxes. Okay, so I'd like you to assume then that the 1 kilogram block does not slide on the 3 kilogram block. So as you're pushing this system, all three blocks are going to have the same acceleration. In other words, there's going to be no slipping between these two. Now we're just saying that we're just saying that that's the case. I'll show you what you do when that's not the case. A little later on, I'll show you. Okay, and then so the questions might be, what is the acceleration of this system if we put 12 newtons on it? This is a frictionless table, horizontal table. We're going to put 12 newtons on this system. What will be its acceleration? And then find all the normal forces. There's a lot of normal forces. There's a normal force between the 2 kilogram block and the table, the 3 kilogram block and the table. There's a normal force between the 2 and the 3 kilograms blocks, and between the 1 and the 3 kilogram block. Okay, so they want us to find the acceleration of the system and then all the normal forces. All right, so here we go. Okay, so the whole idea behind this video is that Newton's laws, Newton's second law, A equals F naught over m, works for any system that you want to call the system. So we could call this our system, or we could call our system this. Or we could say our system is all 3 of them together. And that's convenient to do if they have the same acceleration. That's convenient to do, because then what happens is when we analyze all the forces, the force that the 3 is pushing on the 2 with is equal and opposite to the force that the 2 is pushing on the 3 with. In other words, this pushes on that pushes on this, and since those Newton's third law says that those have to be equal and opposite, then they cancel. So let's see, the forces between these two are going to cancel, and between these two are going to cancel, And so we're gonna just have, if we apply, our system is all three of these together, then the acceleration is going to be the net force. Now the net force in the acceleration in the x direction is going to be the net force in the x direction. Now let's see, we have this force, the 12 Newton. We have a force of friction on the 1 kilogram going this way. There's a force of friction going that way. But then there's an equal and opposite force of friction going this way on the 3 kilogram one, and they cancel because of Newton's third law. So those two forces of friction cancel, so I don't have to worry about them. They're going to cancel out. And so the only forces that are the net force in the x direction is the 12 Newton force. So the net force in the x direction divided by the mass will give me the acceleration. And so the mass of the system, this is my total system. So I'm looking at the total thing at first, and I'm saying that the acceleration, what we should expect, is the 12 newtons divided by 2 plus 3, so that's 6 kilograms. Of course, I set that up so it would be a nice number. Okay, so that's 2 meters per second squared. All right. Now, so we just found out what the acceleration of the system is. The question is, what is the acceleration of the system? It's 2 meters per second squared. Okay, now find all the normal forces. Okay, well, let's see. There's a normal force. Let's see. There's 20 newtons on this block down, and so the force from the table upward has to be 20 newtons since there's no acceleration in the y direction. So the acceleration in the y direction is 0. So that means that all the forces in whatever system you look at, the net force in the y direction has to be equal to 0. Because they all have, none of these have accelerations in the y direction. Okay, so if I want to know, though, what the normal force is, say, of the 3 on the 2, then all I have to do is just hone in on the 2 kilogram mass. So now I'm going to use Newton's second law again, and I'm just going to hone in on the 2 kilogram mass. So here goes. So, and this is the whole point of this video, is that when you just look at the 2 kilogram mass, then we do A. Now we know A equals F net over M. This is for the 2 kilogram mass. A of the 2 kilogram mass is the net force on the 2 kilogram mass divided by the mass of it, so 2 kilograms. Okay, so the acceleration is 2 meters per second squared. We figured that out earlier. That's equal to the net force. Now, if I draw the forces on the 2 kilogram mass, let me put them right here. Let me put the forces right here. They're going to be 20 newtons down. Table's pushing up with 20 newtons. I know that's true because it's not accelerating in the y direction. So this is the normal force, and this is the force of gravity on the 2 kilogram one. And then we have a force of 12 newtons pushing this way, and then we have the force from the 3 kilogram one pushing that way. We'll call that the normal force on it. And so to find that normal force, I'm just going to say that's 12 newtons. And this is the acceleration in the x direction, so the net force is 12 newtons minus Fn all over 2 kilograms. So this is going to be 4 newtons when I bring it over to the other side. 2 kilograms times 2 meters per second squared gives you 4 newtons, and that's equal to 12 newtons minus Fn. And so Fn is going to have to be equal to 8 newtons. So the normal force there is 8 newtons. Now, we just figured out the force that the 3 is pushing on the 2 with, 8 newtons that way. But that means that because of the third law, the 2 must be pushing on the 3 with 8 newtons of force. Okay, well, if that's the case, then I just found the normal force on the 3 kilogram one, and now I can also find what the force of friction is on the 3 kilogram one. Now there's 2 ways I can find this force of friction on the 3 kilogram one. This force of friction is this way on the 3. That's the force of friction on the 3 kilogram one. The force of friction on the 1 kilogram one is going that way. Let me explain that a little more clearly. Well, I'll try at least. So imagine that this box has all these little green, like these little nooks and crannies in it, the 3 kilogram block. And the 1 kilogram block that's sitting on top of it also has these nooks and crannies. So here are the nooks and crannies of the 3 kilogram one. And then here are the nooks and crannies of the 1 kilogram one. So watch what happens when they accelerate together. Do you see how the bottom box, this hand, is going to put a force on the top box that way? Do you see that? It's going that way when it gets pushed. But this force, this box is going to put a frictional force on this hand that way. Watch. So when it gets pushed, this hand, this top hand, is pushing that way on that box. It's a little tricky. Think about that for a moment, to make sense of that. Okay, so there's two ways I can find that force of friction. They have to be equal because they're action-reaction pairs. And so I could do the easy way. I could just do Newton's first law on this one. There's only, let's see, if I look at the 1 kilogram block, there's a 10 Newton force down, because I'm getting that by 1 kilogram times g is, I'm saying, is 10 meters per second squared. So that's how I'm getting 10 newtons down. And then there's a 10 Newton up. That's the normal force, because we know that because it's not accelerating upward. And then there's this force of friction this way. That's the net force. And so let me apply Newton's second law there. So Newton's second law is going to say that the acceleration, 2 meters per second squared, we know that from the previous problem, is equal to the net force, the force of friction, all over the mass. So this mass is 1 kilogram. So the force of friction is 2 newtons rather. If I solve for that, it's 2 newtons. All right, so, but let me just show you that if we looked at the 3 kilogram system, just focused, honed in on the 3, just focus on that, don't worry about anything else. If I do that, then watch how this works. A is equal to the net force over the mass. And so I'm going to say A, the acceleration is 2 meters per second squared, is equal to the net force. Now the net force on the 3, can I put that, let's put the free body diagram of the 3 here. There's a lot going on with the 3. It's got, let me draw it right on the diagram. Okay, there's a lot of forces on this 3. Let's see, what are they? There's a 30 Newton force down from the earth pulling. There's a 10 Newton down because of this block is pushing down on that one with a normal force of 10 newtons, so I'll put 10 newtons there. Those are downward. Upward, there has to be a force upward then, so for it to not accelerate that way, 40 newtons. We know that because it's not accelerating. And then there's this force this way that I already know is 8 newtons. And then there's this force of friction this way. So there's a lot of forces on that 3 kilogram one. And the point of this video is to show you that if you just look at that one and look at all the forces, we're going to have 8 newtons to the right minus the force of friction. We know that's 2 newtons, but let's assume we don't know it's 2 newtons. Divide it by the system that I've chosen, the 3 kilogram one. The 3 kilogram one is this. And now let me solve for the force of friction. So if I bring the 3 on, if I multiply both sides by 3, I get 6 newtons here. Is equal to 8 newtons times the force of, minus the force of friction. So that means the force of friction is again 2 newtons. If you solve for the force of friction, it's 2 newtons. So the whole point of this is that Newton's laws works for any system that you want to pick. Okay? So that's the point of this. Let's try one more. Maybe you can see if you can figure these out. For this one, as just another example. So I think in another video I'll do the same thing, but show you how you handle this if there is slipping. It's pretty much the same thing. but I'll give you some details, and I'll do a problem on how you handle that. But let's just do one more problem. Let's say you have a 1 kilogram block, a 2 kilogram block, a 2 kilogram block, and a 1 kilogram block. There's no slipping here, so everything's going to accelerate to the right on this horizontal table. It's frictionless, just to make things a little easier. All right. And so let's first find the acceleration of the whole system by looking at the entire system. So I'm going to look at this as just one big block, since they all have the same acceleration. So here goes. The system's acceleration is going to be the net force on it. Okay, so we got a bunch of interactions, like the normal force between, there's a normal force of this one on this one, and this one on that one, and so on. But those are all internal forces. So the frictional force, there's two frictional forces. There's a frictional force of heat on the 1 kilogram to the right, and a frictional force on the 2 kilogram one to the left, because of this thing again. And so, but all those are going to cancel. And so all the y forces will cancel, because it's not going to accelerate in the y direction. And so what we have is the net force. If we use the entire system, all those internal forces cancel, and I'm left with 18 newtons of net force divided by the amount of mass. So my system's mass is 6 kilograms. So this time we have an acceleration of 3 meters per second squared. Okay, do you want to see if you can turn off the video and see if you can find like what the force friction must be on the 1 kilogram block? And can you find what the normal forces will be between these two blocks? I'll see you in a little bit. Okay, so let's see, to get the force that the 2 is going to push on the 1 with, let's have just the 1 be our system. So I'm just going to focus in on the 1. That's going to be our system. So I'm going to say the acceleration, which I know, of the 1 kilogram block is 3 meters per second squared. So I'm only looking at this guy. And so the acceleration is 3 meters per second squared. Now we have 10 newtons down and 10 newtons up that are going to cancel each other. We have an 18 newton this way, and then we have a normal force from this block that way. So let's see, we got 18 newtons minus the normal force from the 2 kilogram block, this 2 kilogram block. And then I'm going to divide that, so A equals F net over M. Now the M is, I'm just looking, that's my system. So I'm only looking at that right there. So my system is a 1 kilogram mass. Isn't that neat how you can just look at a particular part of it and Newton's law still applies? Okay, so bring the 1 kilogram to the other side. That's going to make that 3 newtons. If you multiply both sides by 1 kilogram, that's going to equal 18 newtons minus Fn. So Fn, the normal force between these, is 15 newtons. What I'm telling you is that that block is pushing on the 1 with 15 newtons. So the 1 is pushing on the 2 with 15 newtons. Okay? Now, so I already know what force this 1 is pushing on the 2 with. Wonder how much force this 2 pushes on this 2 kilogram block with. Well, to get that, there's a bunch of ways we can do that. You want to see if you can turn off the video for a moment and see if you can figure out how much force the 2 is pushing on how much this block, this middle block, is pushing on this end block with. Okay, so there's a bunch of ways you can do this. I think, gosh, maybe you could choose this system. That would work. You could choose this system. That would work. You could choose this system. That would work. Probably wouldn't want to choose this system because you don't know the force of friction from that yet. Alright, so I'll choose this system. That's going to be my system. Okay, so I'm only looking at that. Okay, now I already know that if I look at all the forces, it's like this is 3 kilograms. So there's 30 newtons down, 30 newtons up. There's a force this way on it. And so if I draw the free body diagram of this 3 kilogram mass, there's going to be 30 newtons down, and then there's 30 newtons up, but I don't really have to worry about those. And so, but there is this force, and that's the force, the normal force of the 2 kilogram on this one. That's the force this is putting on that. And I don't know what that is, but I'm about to find it out. So A of the system is 3 meters per second squared. That's equal to the net force on the system, which is just the normal force. So this Fn is not net, it's normal. It's the normal force. And then divide it by 3 kilograms. You always have to put the system's mass that you're looking at. So we're only looking at that. Okay, bring this to the other side. So the normal force is 9 newtons. All right, and now I can get the force friction on this guy. Actually, I could have even before that. In fact, the easiest way to get that force friction, I'll get it 2 ways, and then I'll say that I'm done with this video. Okay, the easiest way to get this force friction is on the 1 kilogram mass is to look at the 1 kilogram mass. So if you only look at the 1 kilogram mass, and that's your system, so we're not looking at anything else, just the 1 kilogram mass, then we have a 10 newtons down, a 10 newtons up. I'm getting 10 newtons because I'm multiplying 1 kilogram times g, so that's how I'm getting 10 newtons. So 10 newtons down, and there's 10 newtons up from the normal force. And then there's no force to the left on this thing. There's just a force to the right, and that's the force of friction. That's this force. I don't know if you get what I'm saying here, but here's the bottom block. The ridges, the ridges, if you honed in on the surface of that, you'd have these ridges. That's what friction is that they interconnect. And so when the 2 kilogram block goes, see how it kind of carries along the 1 kilogram? Do you see that it's pulling the 1 kilogram this way? Like the force friction's that way. Okay, so that force of friction is the net force. And so A, 3 meters per second squared, that's the acceleration, is equal to the net force, the force of friction, divided by the mass of the system I'm looking at, 1 kilogram. So the force of friction is 15 newtons. That's 15 newtons, I'm sorry. It's 3 newtons. Bring the 1 on the other side, multiply both sides by 1 kilogram, you get 3 newtons. Now, could we have done that another way? Could we have looked at just this block, let's say? Actually, there's a bunch of ways you can do this, but let's just look at this one block, like this block right there. Let's just look at that. Okay, so I'm going to say A equals, now there's some forces on this block. Let me show you all the forces on this block. There's 20 newtons down, the Earth's pulling on the block with that much force, force of gravity. There's a force, a normal force pushing down from the 1 kilogram down with 10 newtons. The frictionless table is pushing up with 30 newtons. I know that because they have to balance out because it's not accelerating up or down. Okay, now there's the normal force from this guy that I know already. And what did we get for that normal force from that guy? It was 9 newtons. Yeah, it was 9 newtons. And then there's this force friction this way. See how the force friction now is to the left instead of to the right because we're talking about this block. And when this goes, you see how this hand up here is pushing that way. That block is pushing actually that way on them. And so so the 3 meters per second squared, I don't have enough room. Let's start over. 3 meters per second squared is equal to 9 newtons. I got that wrong. It's is it 9 or is it 15 newtons? Yeah, it's 9 newtons. It is 9 newtons. Okay, so that's 9 newtons from this part of the problem. Okay, so that's 9 newtons, and so I'm going to say that that's going to be 9 newtons minus the force of friction. And then when I divide by my system's mass is 2 kilograms. So it's going to be 2 kilograms. So if I multiply both sides by 2 kilograms, I'm going to get 6 newtons is equal to 9 newtons minus the force of friction. So the force of friction, when you solve for that, is 3 newtons. So we both ways we got 3 newtons. So here's the point. The point to summarize this is it doesn't, like Newton's laws works for any system that you look at. And so the fun part about doing Newton's laws with double body problems is trying to figure out what system is the best system or a workable system to get you the answer. Many times there's a lot of ways to go with it. All right. Well, I'll see you in the next video where I tell you how, it's going to be a couple days before I get to it, but it's where I tell you what to do if this box is actually slipping on this one. All right. See you later.